so it doesn't cut off in the middle of the lecture. And this usually seems to help for some reason if I start recording really early. So there we go. Just want to make you guys aware since you're talking. I don't want you to say anything you don't want recorded.
Good. Oh my God, I left. I'm sorry. I'm just happy I have a suit.
My independent.
Yeah, I think mine should go up too. And plus, we're also going to do some studying together for the finals, so it should help.
Interesting.
No. Oh. I know we're chapter 9. So we just have an introduction to that.
My regular is not working, and I've got to be enthusiastic after this.
Well, we might have an issue. We'll see.
Well,
Well, at least you guys have computers.
Yeah,
we can share.
So even
Yeah,
though
we can share.
I'll be talking to you, but it might be showing up on your computers instead of there. We'll see.
I can see.
So annoying.
Gobble up technology.
My laptop is at home and does. Oh my God. What are we doing, Dr. with this? That's what I want to know. It's like final.
Got it.
Yay!
I can fix a jet. I can fix a projector.
Okay, we're in module
15.
we're in 15. Extra. As you're working on your mission. Oh yeah, we're turning in our final philosophy.
So what's that going to be?
You know when we turn in like a rough draft or whatever, we're gonna revise it and then. I did really good on that. Hopefully that sets me right where I need to be. Let's see what my grades are. I think I'm on Friday.
All right, Van Cross. Taylor's here. Wait, yep, is here. Michaela's here. Bowers. Asbury.
Here.
Oh, there you are. Tudor. Burdette. Newton. Massey. Richardson. Cedric. Rice. Midkiff is here. Eric. Hodges is here. Justin. Let's see. Oh, yeah, thanks. Yeah, so Rice, make sure you send me the attendance words. You know, it's partial credit, but partial credit's better than, it'll be more than, it's like 3/4 credit, which is better than half credit.
I have a question about how we just joined this meeting.
Good question, and I'm glad you asked because we're recording. Of course, it doesn't matter this late in the game, but yeah, the same way you would meet online for class is the same way you would meet me online for office hours. Yeah, just click the same link and I'll be there. Let's see, 7:58. So I'm going to try to do less important announcements. I want to wait till everybody's here to get the really important ones. So to remind you again, lab this week is you just choose whichever past lab you want as your new grade, your grade for this week, and let me know which one it is. So again, if you have a perfect lab and you just want to use that grade and don't want to do any work because you have other important things to do this last week of class, then use that lab. Or if you have a lab that's really bad that you want to fix, tell me that's the one you're going to do and let me know when you're done doing it, and then I can regrade it. So you'll get that new grade for this week, and it'll fix the grade for whichever week that you did it. And if you want help choosing which grade or which lab you should do, yeah, like she was sort of asking, meet me online for office hours and we can look at all your labs and figure out which is best. What else? Yeah, that's it for lab. Any questions about labs? So again, we won't be meeting for lab this week. It's the last week of class. I wanted to make things easier for you so you can focus on the final and whatever else you might have going on in other classes. What else? Labs. Speaking of the final, I already said this in writing, but I'll go ahead and tell you now again verbally. The final is on Monday. It is from 8 to 9:50. It will be online. If you prefer for it to be in person, let me know beforehand, so I can print it out and we can meet here in person. If you want to take it some other time, let me know beforehand so we can make arrangements for that. Because I don't care when you take it, as long as it's done before Thursday, because that's when finals end. Doesn't matter to me. So yeah, let me know if you want to take it some other time. What else? And again, it's about 100 questions. About 50 of those questions come verbatim from the first 3 exams. I'm going to copy and paste them. Not going to change them. Not going to reword them. So you should be studying your first 3 exams. Speaking of which, that's a good reminder too. As of today, as of the end of today, it'll be too late to retake any of the old exams, because after that, starting today, I'm going to start giving answers. Like if you meet me online, I can give you the answers for the first 3 exams. And the 5% boost to your grade for getting feedback for the exam. So yeah, any questions about the final exam? So study your old exams and study the last 3 study guides for the final exam. That'll get you prepared. All right, it's 8 o'clock now, so some more of the more important announcements. I want to apologize. I did this on Facebook and on Google Classroom yesterday. Go ahead and apologize in advance. If you're asking me questions about your grade or sending me stuff that's old, I've got to tell you, it'll be a while before I get to you. It's the end of the semester. Everyone waited until, not everyone, a lot of people waited until the last minute to turn in independent work. A lot of people wait till the last minute to turn in, old stuff. Not just your class, but other classes too. So I've got a lot of grading to do. I'll get to your stuff when I can. But obviously, to remind you, it is now too late to turn in independent work. Last night was the cutoff. However, moving forward for the next week, you still can do videos and things like that, because it doesn't take as much time to grade those, because they're multiple choice and I get the grades. So you can do the videos, things like that. You just can't do any more papers. And the only other catch is I can't guarantee I'll grade it, because again, I'm getting swamped with a bunch of stuff. So if you turn in 5 videos that you watched this week, I'm going to try my best to get to them and grade them, but I can't guarantee you that I can. So again, officially the cutoff was last night for independent work. Any questions about independent work or anything in general? All right, really quick, let me finish attendance. David, Eric is here. Cedric is online. Richardson. Richardson's here. Massey, Newton, Burdett, Hudson is here. Felder, Tudor, is here. Sorry, I already called that. And Bowers. I think I called everybody at that point then, right? Everybody's accounted for? Let's jump into it. I'm going to go quickly because, again, we only have 1 week to cover this chapter. So slow me down if you need to, or better yet, if you can, just make a little note and then try to meet me during office hours and say, hey, can you re-explain this concept? Because I'm about to fly. Of course, as I always recommend, even though it's the end of the semester anyway, it doesn't really matter, but you should read the textbook. Basically, I'm just confirming what the textbook says, and if I say something that you thought the textbook said something different, then you can ask me about it, and I could re-explain it. Anyway, chapter 19, we're still talking about ecology, except now, in an odd twist, we're kind of stepping back. So instead of looking at landscapes, which are a bunch of interacting ecosystems like you learned in chapter 20, or ecosystems, or it's a bunch of living things interacting and also how they interact with their environment, we're taking it down and we're looking at populations. So we're backing up a little bit. We won't even go through that. We won't go through this either. But your book is talking about these invasive species. You can look it up if you want. So let's talk about an overview of we did start this, didn't we? I'm sorry. We started this and then jumped into chapter 20. Let me remember where we were. I'm sorry, guys. If you see Here we were, age structure, right? Yes. This is where we were. Yes, we just did the overview. Here we go. Let's jump into it. So population density. Again, we're looking at populations, and like I said at the end of the class on Friday, there's different ways to look at populations. You can look at the density, the age structure, survivorship curves, things like that. So the first thing we're going to talk about is population density. It's a pretty simple concept. You're probably already familiar with it. People talk about it with humans all the time. So when you hear like, this city has this many people per square mile, and this city has that many people per square mile, right? That's population density. It is the number of individuals of a species per unit area or volume of the habitat. So again, if you can just remember that humans are commonly referred to when we talk about the population as X many people per square mile, then you can remember the rest. Of course, your book does point out, and I like this, that when we talk about humans, then yeah, that's like per square mile, but sometimes it could be different. For example, if you're talking about fish, right, it's not square mile, it's a cubic, right? Because it's not just like the surface, it's also how deep it is. So in that case, largemouth bass per cubic kilometer, or oak trees per square kilometer, or nematodes per cubic meter. These are all examples from your book. You don't need to know any of them. You don't need to know any examples. The point here is population density, again, is the number of individuals in the species per unit area or volume of the habitat. If you click this link right here, you can watch a little video on YouTube that talks about human population density using humans as an example. But again, I'm not going to ask you any of those questions. There is one question on the study guide about this. I forget exactly how it's worded, but go ahead and take a look at the Chapter 19 study guide. You'll see the question about population density on there, and then you'll see if there is a question on the final about population density, that's how it's going to work. It's a very simple math question. But anyway, any questions about that? Let's say the first word for attendance is oak, like an oak tree. How do we measure population density? I'm going to go through this very quickly. I'm not going to ask you any of this. This is just for your own knowledge. That's why, again, I'm putting the X to indicate I won't ask any questions about this on the example. But in most cases, like for humans, it makes sense, right? We do a census every, 4 years or is it 2 years? I actually forget. Anyway, we know exactly how many humans, for the most part, are in the United States. That part's easy. But if we're talking about nature, it's a little bit harder, right? It's impractical or impossible to count all the individuals in a population. So instead, we do things like, all right, so if an ornithologist knows about a particular species of bird, they know how big their territory is, they know how territorial they are, they know what their nests look like. So if they could count the number of bird nests, and they would know these things because they're ornithologists and they would know that they belong to those species, they could say, all right, if there's this many birds' nests in this 1 square mile area, then they can estimate how many birds are in that area. Or again, same thing with here, rodent burrows, which will be the next picture I show you. The groundhogs, you can't really count groundhogs. They're always popping up and down, right? That doesn't work. But they know how deep most, if they see one hole, they know how big that hole probably is, and they know how many groundhogs it probably holds. So then they could do a good estimation from that. So again, there won't be any questions about this on the exam. It's just pointing out that when we're doing population density or even just counting the population at all for most of nature, it's not as easy as it is for humans. So again, there's a bunch of groundhogs. They have holes. They pop in and out. It would be almost impossible to figure out exactly how many there are, but you could make good estimations based on the research people have done before, right? Somebody first probably figured out the average number of groundhogs per hole. And then from that, they could use that as a way of calculating the population. Any questions about that? All right, population age structure. This is probably most important for you guys who are not biology majors, depending on what your what your major is, because this is actually relevant to humans in addition to just nature in general. We'll talk about why. First of all, you need to know what the age structure is. And the age structure of a population is the distribution of individuals in different age groups. So for example, if I were to say, all right, West Virginia is primarily old people with a slightly lower number of middle-aged people, and even lower number of young people, young adults, and a high number of children. And I don't know I'm just making that up, right? But what I just described there is the age structure. So we're not talking about the density, right? We're not talking about how many people per unit area. We're talking about the age structure, right? Is there a lot of young? Is there a lot of old? Is there a lot of in between? Is it even all throughout? The reason this is important for biology is because it provides insight to the history of a population survival, and I'll give you an example of that moving forward. It's reproductive success. Again, that'll be in the same example. How the population relates to environmental factors. Again, I'll give you a slide for the next example. You don't need to understand the insights. This is for your own knowledge. What you need to understand is what the age structure is. And again, eventually in this chapter, I'm going to briefly talk about how the age structure is relevant to non-biology majors. I guess I could kind of do it now. Like, how many of you are any criminal justice majors? No? Okay. Any business majors? Okay, so that would be relevant to you, right? Because, well, depending on what kind of business you're into. But if you're looking at like marketing or advertising or something like that, or just the need for a business, it helps to know the age structure, right, of a certain area. Like if there's a lot of old people in a certain area, you're probably going to want one certain kind of business. I don't know what that would be. Versus if there's a lot of kids in another area, you might want things like Chuck E. Cheese's and stuff like that. But anyway, any questions about this slide? So here we go. Here's an example. Here we have the age and years. So they looked at this species of bird. I forget what kind it is. It doesn't matter. And they were looking at them, and of all the birds they found, they ranged from ages 1 to age 11. And you can see the percentage, right? So in this population, a large percent, the largest percent anyway, were ages 4 years old. So you might be thinking, how is this useful? And for you guys, it isn't because you're not biology majors. But if you're an ornithologist and you just got to this area and you weren't trying to figure out how this, the things that affect this population, but you just started studying them, you could look at this and then compare it to data that somebody else might have, right? So you could look at weather data, for example, or climate. And you could look at this and say, okay, 10 years ago, something really bad must have happened. And same thing with 3 years ago and 2 years ago, right? And 4 years ago, something must have been really good. So just given this information, you could just look at, I don't know, again, climate. And you could say, well, I noticed that for both 2, 3, and 10 years ago, summer started, meteorologically, summer started 5 weeks early or whatever it may be, right? So then you could look at that information, that information and put them together and say, obviously this bird species doesn't do well when summer starts early or whatever it may be, or rainfall patterns, or maybe the possibilities are endless. But you guys see what I'm saying, right? You can see which years were successful, which years were not. And by looking at that, you could compare other data and figure some things out. Anyway, that's just an example. I'm not going to ask you any questions about that on the exam, obviously. If anything, and again, as you guys know by now, I don't do this often, but if anything, I could show you this picture and then ask you to decipher this and say, which year was really good for this bird species, or how long ago? And you could look at this and say, again, 4 years. Or in which year were things really bad? 10 years ago, 3 years ago, 2 years ago. And which year did the population, well, I'm wasting enough time on that. Anyway, any questions about that? Trying to move quickly. All right. So something related to the population age structure is something called the life table and survivorship curves. Life tables, you know what they are. They track the survivorship of a population, and the survivorship is the chances of an individual in a given population surviving to various age groups. Like I would say probably the probability of you guys, how many of you are not in your late teens or early 20s? All right, so you're all in your late teens and early 20s. I would say the probability of you guys hitting your 30s is fairly high. Probably the probability of me hitting the 50s is fairly high, but your chances of getting the 30s are probably a little better than my chances of getting to the 50s. Meanwhile, somebody who's in their 70s, their probability of hitting their 80s is a lot lower. And somebody who is in their 80s, their probability of hitting the 90s is a lot lower, so on and so forth. And that's important for biology because it helps determine the most vulnerable stages of the life cycle, which for humans almost doesn't matter. I mean, it does because obviously we care about humans. But for us, it's just very common sense. Like we know at what age things start to deteriorate for humans. But if you're studying a population that nobody else has studied before or very few people, then it's important. Because not all things are like humans, right? It's not all like your chances of growing old are high, but once you get there, your chances of survival start plummeting. It's not like that. It's actually quite different for other species. Anyway, for the exam, again, you need to know what a life table, you need to know these 2 bullet points. What a life table is and what survivorship is. So any questions about this slide before I give you an example? And your book wouldn't with a human example, and this is basically what I was just saying earlier, but now you can visualize it, right? So the chances, this is almost confusing because they like to put a bunch of words and numbers. But if you just really look at this right here, the age interval and this right here, that's your percentage of getting there, right? So your chances of hitting, age 10 after you're born, probably 99.2%. Your chances of getting to your tens or teens is 99.6%. Your chances of then getting to 30s is 99%. You can see how it kind of slowly drops, and then right here it starts dropping really quickly. And that's it. And then we can tell by looking at this that the vulnerable points in a human's life, or I guess I should look at this, 92. Of course, this too, right? It kind of drops right there, and that's where it starts going. So here's a really good time in the human's life as far as your chances of surviving. But anyway, any questions about this? Again, this is an example. So when you're studying your textbook, because I know that's what you guys will be doing this week, don't study this chart. I'm not going to ask you any questions about this. There's nothing to memorize. Survivorship curves. That's the next thing you need to know. That plots the individual still alive at each age in the maximum lifespan. In a way, and this isn't exactly true, but in a way, a survivorship curve is kind of like a graph of the table I just showed you. Sort of. And you'll see what I mean when I show you a picture. It uses percentages instead of actual ages. That way we can compare species that have varying lifespans. So, we could look at humans, which we know, we live to be about what, 70, 80, 90, sometimes 100. You know how long humans live. And then now, because of the natural selection lab that you did a few weeks ago, that those peppered moths live 1 year, right? So it's, in one way, how are you going to compare those two? Because, 1 year versus 80 years. But again, we use a percentage instead of actual ages, so we can compare those two together. And the next slide I'm going to show you actually shows some survivorship curves. And I'll go ahead and tell you now, of course, I'm not going to ask you if it uses percentage scales. I'm just telling you that. That way, when I show you the slide, you know what it means. And I'm probably also not even going to ask you what a survivorship curve is. You're just going to need to know some things about survivorship curves, and I'm about to show you what they are. So here's 3 different survivorship curves, and you're going to need to know the difference between the 3 of them. The first one is humans, or something like a human. In the next slides, I'm going to show you, put all this into writing. Everything I'm about to tell you is going to be put into writing. But humans, right? So again, it's a percentage, right? So instead of having like 0 to 80 years old or whatever the average lifespan is for humans, it's just a percentage, right? So what are the chances of, a human hitting middle age? It's pretty high, right? The chances of survivorship doesn't drop off until you're old. Unlike a type 3 survivorship curve, which is your chances of surviving are like when you're born, or if it's a seed, or seed's a good example. The chances of even getting through life, like starting life, are very low. But then once you make it, then your chances of survivorship are pretty high. They don't really change much. And then you have a type 2 survivorship, which is where your chances of dying from 1 year to the next, they're pretty solid. Right? It's not like 1 year is better than the other. So again, type 1, your chances of growing old are pretty high, and then your survivorship chances really drop. Type 3 is the opposite. Your chances of making it past, I'll say childhood, but obviously oysters don't have children, but you get what I'm saying. And then again, type 2 is steady throughout. And here's this in writing. Type 1, here's some things. This is the part you need to know about survivorship curves. Type 1 survivorship, these organisms, like humans, for example, produce few offspring. They give good parental care, and there's an increasing likelihood that they'll survive to maturity. So the opposite of that, before I talk about type 2, is type 3. Type 3. Yeah, that's why I don't put it in order, because the opposite of type 1 is type 3. That's where there's low survivorship, followed by a period when survivorship is high for the few who live to a certain age. So you guys have seen those maple things that like fall down like helicopters, right? They do that. Those are seeds. And biologically speaking, the best way you could compare a seed to a human is those are babies, right? Because that's the product of the mom tree and the dad tree coming together and producing seeds. So, as you might imagine, those seeds, they produce thousands of them, and most of them don't make it. Most of those seeds just get eaten by a squirrel or get crushed by a car or just rot and turn back into the soil. Very few of them actually grow into a sapling, and then very few of those actually make it to be a full-grown tree. So that's what I mean by low survivorship for the very young, right? They're just spreading the seed, literally, hoping that some of them make it. Anyway, and then in between that is type 2. Again, type 2 is between type 1 and type 3. That is where the survivorship is constant over the lifespan. So again, your book used the squirrels as an example. So any squirrel you see, whatever age it is, its chances of surviving to the next year are just the same as any other time in its life when you would have found it. So again, you do need to know the differences between type 1, type 3, and type 2. Most likely in the exam, I'm not going to ask you to define type 1, type 2, and type 3. Most likely, I'll give you an example. I'll describe some population or some species, and then you, from that description, should recognize it as type 1, type 2, or type 3. Any questions about this slide? Okay, the next word for attendance will be life. Now, speaking of attendance, I'm sure some of you have noticed I haven't posted a video for Friday yet. That's coming. Again, it's the end of the semester, so I'm just swamped with things to grade. All right, next thing we're talking about is life history traits as adaptations. So you kind of learned a little bit, even though I didn't call them that when we were talking about the survivorship curves and all that. Basically, those are some life history traits. I didn't call them that. You're about to learn officially what a life history trait is, and then you're going to learn how that's an evolutionary adaptation. First of all, you need to know what life history is. We'll put a question mark next to this because meaning I'm not sure if I'm going to ask you this on the exam or not, but you need to know what it is because I'm going to talk about it. So if I'm going to talk about it, you know what I'm talking about. Life history is the set of traits that set the schedule of reproduction and survival. So for people who study different species or populations or whatever, because that's what this chapter is about, right? This is just one of the ways that we can describe a population or describe a species. So for humans, set schedule of reproduction. So for humans, right, we would say humans, biologically anyway, are able to start reproducing around mid-teens, right? Biologically, we don't do that, and then when we do it, usually you can only have a kid. A female can usually only has one child at a time, and it's usually maybe about 1 year at a time, right? And again, survival, which is what we talked about earlier. Like, at what age do they usually die? Things like that. Anyway, that's what life history is. So a population's pattern of survivorship is an important feature of its life history. So some key life history traits. So this is expanding on these two right here. Some key life history traits include the age of the first reproduction, which is what I already said for humans. Like once you hit puberty, biologically anyway, that's your age of first reproduction, potentially. The frequency of reproduction. So again, humans, maybe once a year. The number of offspring, so again, usually a human has one at a time. And the amount of parental care given. So again, for the most part, humans take care of their babies. Unlike an oak tree, which just drops a bunch of acorns, right? Those technically are their babies, but they just put a bunch out hoping some of them will make it. I mean, they don't really hope, but you know what I mean. Anyway, this is also a good, never mind. It's too late for independent work. That would have been a good independent work topic. You could have looked up whatever kind of animal or plant that you like and given me life history traits. But anyway, any questions about this side? All right. As you already know from chapter 13, reproductive success is the key to evolutionary success. And a lot of you, because I've been dragging my feet on grading labs for a reason, I did grade the evolution lab this weekend. So a lot of you probably noticed that you got some of these questions wrong. So when you talk about natural selection, remember, it's not just survival. It's also survival and reproduction. So reproductive success is the key to evolutionary success. It's all about passing along those genes. Whatever it is that gave you an advantage, passing along those genes to the next generation, which changes the population. Anyway, the combination of life history traits presents trade-offs and balances between the demands of reproduction and survival. So again, looking at oak trees versus humans, oak trees, they do produce a lot of babies, so to speak, because they put out as many acorns as they can, a lot more babies than humans produce, but most of their babies don't make it, right? But they still put out a lot. They still make a lot of new trees. So again, it's just the balance. Like, do you want a lot of kids that you don't really take care of well, or do you want fewer kids that you take care of well? Anyway, because selective pressures vary, life histories are very diverse. And yeah, as far as the exam is concerned for this chapter, there's probably nothing very important on this slide, but this is a good thing for chapter 13, just to remind you. Again, reproductive success is a key to evolutionary success. So there's different types of life history traits, and we categorize them, of course. We do that probably. And you need to know them. The first one you need to understand is an opportunistic life history. And for the exam, again, I'm not going to ask you to define this. I'll give you an example of this, of some species, and I'll describe it, and you say, oh, yeah, that's opportunistic life history. So if it takes immediate advantage of favorable conditions, and it typically exhibits a type 3 survivorship, that is an opportunistic life history. So for example, dandelions, right? Literally one day you might look out on your grass, your lawn, and see 0 dandelions. Then the next day, or like 2 days later, maybe there's just a bunch of them, right? Because all of a sudden conditions were right, so they grew up quick. They produced these seeds, a lot of little ones, right? Because remember, each one of those, technically, if you're comparing them to humans, each one of those little things is a baby. They produce a bunch of them, they get spread out, and hope that some of them make it. So again, opportunistic life history, type 3 survivorship, takes immediate advantage of favorable conditions. It's kind of in the name, right? It's opportunistic. Any questions about opportunistic life history? The next one that you need to know, the other one you need to know, is equilibrial life history. It's kind of like the opposite. And basically that's the two of them, right? So on the exam, you're going to need to know, when I give you the example, is it opportunistic or is it equilibrial? And also keep in mind, too, you know how my exams work at this point. You'll probably get more points taken off if you guess something other than equilibrial or opportunistic. You'll probably get partial credit if you guess the wrong answer, but at least it's one of the two, one of these two. And you'll probably lose a lot of points if it's some weird word that I just made up. Anyway, let's talk about equilibrial life history. Typically, they reach sexual maturity slowly. So again, humans, puberty, that's relatively slow compared to an opportunistic life history organism. They produce very few well cared for offspring, which kind of goes with this other bullet point. These kind of say the same thing. Typically exhibit a type 1 survivorship. Well, type 1 survivorship, they produce very few well cared for offspring. And they're typically larger bodied and they live longer. I don't remember if these pictures are from your book or not, but these are good examples. Right? Elephants, I think, have the longest gestation period, at least of land mammals. So I think they're pregnant like 22 months or something like that. And they live a long time, and they have relatively few offspring, and they take care of their offspring. And I know this seems weird, but I'm showing you the tree. But in this conversation, this is climbing closer to an equilibrial life history. It's a larger tree. And you compare that to a dandelion, right? Because we're talking about plants. It gets a lot larger than a dandelion. It lives longer than a dandelion. Each one of those coconuts is a seed. So compare that to those little tiny little things that blow away when you blow on a dandelion, right? So those technically are well cared for offspring because they're big for a reason. They've got a lot of protection and a lot of protein and a lot of liquid to protect them. So again, for the exam, you'll need to know the difference between opportunistic life history and equilibrial life history. And I'm not going to ask you to define either one of them. I'm going to give you an example, and you need to recognize one over the other. So, any questions about that? And then before we move on, this, if you're studying it, this is what you should study, right? Because again, you can know the difference between the two. If you just study this, then you should be fine. They're basically opposites of each other. Where can you usually find them? I don't like this because in almost any climate, you're going to be able to find both, right? You're going to find some that are opportunistic and some that are equilibrial. But how long does it take them to mature? If it's opportunistic, they do it quickly. If it's equilibrial, it takes a long time. You can read all this. Again, it's a multiple choice exam, so you don't have to memorize this whole thing. Just kind of get familiar with it, because when I give you an example that includes some of those things in that column, you just say, yep, I recognize that as opportunistic or equilibrial. All right. So we're done with the first major bullet point. Let's get to the second one. This one's actually kind of, in my opinion, a little bit easier. This is, in my opinion, there's a lot of common sense stuff. And I'm just going to be giving you words to things that you're probably like, oh, yeah, I knew that was a thing. That makes sense. But go figure, there's a word for it. As you know, in case you didn't know, the population size fluctuates. Actually, that might be a little bit trickier, I guess, maybe. Because if you don't think about things in terms of biology, when you think of population, you probably just think of a growing population, because that's what the human population does. It grows, it grows, it grows. But if we're talking about other populations, other organisms, other animals or plants or fungi, whatever, it fluctuates. It goes up, it goes down. What causes it? And you do need to know this, and this is very simple. And if you've had Bio 108, this is a repeat for you. Common sense stuff here. What makes a population size fluctuate? Well, it can go up as new individuals are born or things migrate in. And it can go down as individuals die or things migrate out. Pretty simple, right? So models investigate how the size of a population may change over time under different conditions. This bullet point is not a test question. It's just a segue into what I'm about to teach you. We're going to talk about the things that makes a population size fluctuate. What affects people or things being born? What affects things dying? So any questions about this side? All right, I will say this. For the exam, again, when we're talking about population growth models, it's basically just these two, exponential and logistic. And just like all the other stuff I've taught you so far in this chapter, you need to know the difference between the two of them. And again, just like the other stuff I've taught you in this chapter, that's probably not that I'm going to ask you the definition. It's probably I'm going to give you an example, and you need to recognize it as either exponential or logistic. Exponential population growth. That is the expansion in an ideal and unlimited environment. Hypothetically, unlimited environment. Technically, there is no such thing as an unlimited environment, right? Because there is a finite amount of mass of stuff on Earth. So there is technically no unlimited environment. Anyway, this is when the population size of each new generation is calculated by multiplying the current population by a constant factor that represents birth rate minus death rate. A really fancy way of saying is this going up really quickly, right? So let's say humans, and I don't remember the exact number, it does fluctuate. Let's say humans, where is it at? Multiply current population by constant factor. Let's say our constant factor was 2. Right, so for every human born, there's 2. You just multiply the population by 2. So if there's 100 humans now, then in the next generation there's going to be 200 humans, and then in the next generation after that there's going to be 400 humans. Next generation after that, 800, so on and so forth. That's what I mean by multiplied by a constant factor. Basically, in layman's terms, when we're talking about this, if we're talking about exponential population growth, I'm saying it's going up really quickly and not going down. Speaking of which, that accelerating growth produces a J-shaped curve. So if there was a graph right here, and we're looking at the population, right? So here's, years on the x-axis, and here's the number of individuals in the population. When it goes up, and it goes up quickly, that's the J-shaped curve. So yes, for the exam, again, I'm probably not going to specifically ask you, but if I describe something as having a J-shaped curve, you used to say, oh, that's exponential growth. And of course, the slope shows how rapid, come on, good grief. The slope shows how rapidly the population is growing. Here we go again. There we go. So for example, again, if I had a graph and said, all right, good, what? This is so annoying. Anyway, are you kidding? Sorry, guys. If we had a graph showing the growth of 2 different populations on the same graph, they both had a J-shaped curve, and the computer never worked. Good grief. This would only happen on the last week of class. Sorry, guys. Well, we just try unplugging it, plugging it back in. Hey, maybe this will work. Anyway, again, if you had a graph and one population had an exponential growth like that, forget those horizontal lines, that's an accident. And then another one had an exponential growth like this, right? So that's population A, that's population B. And you might have a question like this on the exam. And I said, which population is growing quicker? Population A or population B? The answer is A, right? A They're both exponential. They're both going up quickly, but you can see A is going quicker than B. Make sense? Pretty simple stuff. All right. So exponential growth is common in situations, and I'm probably not going to ask you about this, probably. This is for your own knowledge, but this is usually common in certain situations following a disturbance. And I like this, right? Because we talked about disturbances in chapter 20, so I don't have to teach you what a disturbance is here in chapter 19. But yeah, so again, if we have a fire or a flood, hurricane, drought, cold snap, nuclear bomb, volcano, whatever, if we wipe out a lot of a population, then we sort of have an ideal unlimited environment, right? So the population is just going to explode, at least at first. Any questions about this side? All right. This is just an example. Again, there's that J-shaped curve. 98% chance I'm not going to give you this graph on the exam. But if I did, again, it might be some stupid 5th grade thing. Or like, all right, in 7 months, what was the population? Like it's 7 months, and go up here, and it's between 100 and 150, so maybe 125, right? Good old elementary school stuff, but again, probably not. All right, so that was exponential growth pattern. The other one is logistic growth pattern. And before I describe it the way the book describes it, here's how I describe it. In my opinion, it's always exponential at first, right? You're always going to grow at first, but then obviously things are going to happen and you're going to stop growing. And that's what the logistic population growth model is. It's when it stops growing. That's how I describe it. Let's talk about how your book and everyone else describes it. Going back to what I was saying, most environments are not unlimited. Because remember, when I said exponential growth, I said it was an unlimited environment. But that's usually not the case. Obviously, technically, it's never the case. Nothing is unlimited. Because there's things called limiting factors, and you learned about those in chapter 20. So I can go through this really quickly. A limiting factor is an environmental factor that restricts the population growth and controls the number of individuals that can occupy a habitat. Again, going back to my sugar cookie analogy, if you had all the different ingredients, you make sugar cookies for a living and you have just warehouses and warehouses full of the other ingredients, but you get a dozen eggs a day, then that's your limiting factor, right? You've got plenty of the other stuff, but you can only make so many cookies because you only get so many eggs. That would be the limiting factor. And in biology, it's whatever it is in the environment that's keeping that population from growing. And that brings us to a term you definitely need to know, carrying capacity. And again, if you've had 108, this is definitely a review for you because carrying capacity is very important in that course. It's a little bit less important in this class. It is the maximum size a particular environment can sustain, which is weird because humans, we don't really think about that. We just think, well, we grow and we grow and we grow, and as we get larger, we just make it work. But in almost every other population, for every other organism, it doesn't work that way. There's a set limit. Actually, there's probably a set limit for humans too. People argue about that, what exactly it is. We're not there yet, but we're probably getting close. So that's what the carrying capacity is, right? It's the maximum number. Like I bet you if you were to count the squirrels on WVSU's campus, I would assume they're probably at carrying capacity. It's probably maxed out. Anyway, that brings us to another term you need to understand, which is logistic growth. That is when the growth rate decreases as the population approaches carrying capacity. This will make a lot more sense when I show you a picture of it, when I show you the graph. But again, what we're talking about right now is the logistic population growth model. So there's exponential growth and there's logistic growth. So this is the main thing that we're talking about here. And again, I describe it as, like I said earlier, it always starts off exponential, but then eventually it starts leveling off, and that's what logistic growth is. Yeah. So again, for the exam, you have to understand carrying capacity is the max number that any area can sustain for a particular population, and logistic growth is what we're talking about, right? That's when things start evening off. And I'll show you, it makes a lot more sense when I show you. So you can see here, if I were to cut this graph off right here, right, and you're only looking at that, and I said, what is that? You hopefully would say, oh, that J-shaped curve, that's exponential growth, because it was at first, right? But then it starts limiting, right? In this case, if I remember correctly, your book is talking about these seals, and they all live on the same island. So in that case, the limiting factor is literally a place to live. They run out of space. So anyway, this is the actual population. These dots represent the data. And you can see it's not all exactly on the line. This is just a model. This is what we expect the population to do. You can see sometimes it goes above the carrying capacity, which is right here. But then because it's above the carrying capacity, it'll drop back down below it, and it fluctuates. And if we were to carry this back, look, this is 1945. I bet you if you were to carry this off into 2023, that line would still stay the same, but you would probably see the dots above it and below it, right? Sometimes it goes up, sometimes it goes down. But overall, on average, it stays right there at the carrying capacity. Obviously, again, this is an example. There's no need to study this graph. I'm not going to ask you questions about breeding male fur seals. But are there any questions about this? All right, so the next slide I'm going to show you compares logistic growth with exponential growth, which are the two different ones you need to know for the exam. You need to be able to recognize one versus over the other. And again, like I just said, they're both theoretical ideas of population growth. So again, that red line was the theoretical idea. That's the model versus the data, the black dots, which are the actual data. So again, there we go. There's carrying capacity of a rabbit versus those seals. And again, it had this, I don't know. Eventually, that rabbit also is going to hit logistic growth, and eventually that exponential growth will turn into logistic growth. It's either that or one of the other options that I'm about to teach you, but nothing can stay in exponential growth forever. Any questions about this slide? So again, and you definitely take a look at the study guide because some of those questions might be on the exam. But one of the ways you can differentiate between the two, you have the J-shaped curve for exponential growth and an S-shaped curve for logistic growth. All right, so what are some of the things that affect these population growths? That's what we're going to talk about. So like I said earlier, there's these things called limiting factors that limit the growth of a population. And now I'm telling you there's some subcategories. So when we're talking about limiting factors, there's different types. One of them is called a density dependent factor. And it's kind of in the name. Hopefully this is really simple for you. It's when the intensity of the limiting factor is related to the population density. Of course, that second bullet point kind of goes without saying. That's what we're talking about. Yes, of course, it can limit the growth of natural populations. That's exactly, I should probably eliminate that from the PowerPoint because we're talking about a limiting factor. So this bullet point kind of defines what a limiting factor is again. So the key here, again, if it's density dependent, the intensity of this factor is related to population density. So think about like COVID, right? Back when it was really new. COVID probably spread through a place like New York City a lot quicker than it spread through a place like South Dakota because of the population density, right? Diseases need things to be close so they can spread from one organism to the next. Another example that your book gives is intraspecific competition. Notice that's intra, not inter. So inter-specific competition, which is what you learned in chapter 20, is competition between different species. Intra-specific is in the same competition between the same species. So again, you can see these wolves competing over that carcass, right? So obviously, the denser your population, the more competition you have between your own population. And again, for the exam, most likely, I'm not going to ask you the definition of a density-dependent factor. I'm going to describe some factor, and you need to recognize it as density-dependent or density-independent, as I'll teach you later. So just think, if it's the population density would affect it, then that would be density-dependent. For example, well, I'll tell you this when we move forward. So that's density-dependent. Again, it's all about how dense the population is. Any questions so far about that? The next word for attendance, let's say wolf, since we have two of them up there. Wolf. This is stupid too. I don't know why I put this on there. They both can do this. Yes, a density-dependent factor can lower birth rates and increase death rates. But then again, so could density-independent factors, right? Because that's the whole thing. We're talking about things that limit the population. So I'm going to put two X's through this. One, because I'm not going to ask you. But two, because really, that's not really unique to density-dependent factors. However, some examples from your book, the accumulation of toxic waste products, right? So if you have, I don't know, certain bacteria growing or a mold growing on a thing, some of the product, some of the things that produces in its everyday living can get too toxic, and then eventually you'll kill some other ones off. Again, like I already talked about, COVID was an example of disease transmission. You have a high population density, you have a lot of things crowded together, it's going to be easier for that disease to pass from one to the other. Food, obviously the more squirrels on WVSU's campus there are, the less food they have individually, right? Because they're competing with each other, that interest-specific competition. Same with water, same with shelter, right? Places to hide, places to raise your young. Those are just examples. I'm not going to ask you any of these examples. The point is, I'm going to describe some situation, and you need to recognize it as a density-dependent or density-independent factor. So are there any questions about this slide? This one's a little bit more complicated. I'm just going to briefly talk about it. I'm not going to ask you any questions about it. It's a great example, though. So what we have here is this bird, and this is the density of females, right? So here, there's very few birds per square mile, if you will. I don't know what the unit is. It doesn't matter. Anyway, they're not very dense, and here the population is really dense. There's a lot of birds in a small area as you move that way. Here is the mean number of offspring per female. So basically, as things get more crowded, they have fewer and fewer. They lay, we won't say they lay fewer eggs. They probably lay the same number of eggs. Maybe they don't. I don't know. But for whatever reason, they have fewer offspring. Maybe they don't lay fewer eggs. Maybe because it's such competition to find a place to make a nest and lay your eggs. Maybe because of that, some of them don't even have a place to lay their eggs. Therefore, they have fewer offspring. Does that make sense? You can see here how population density would keep them from finding a place to have their offspring. Here's kind of the opposite. So this is, you can see how population density decreases the birth rate. Here's the other side of the coin. This is how population density increases the death rate. So here we have these fish. They live in the kelp. They hide in the kelp. That keeps them from being eaten. Obviously, as population density increases, there's more fish in the same area. There's fewer places to hide. Therefore, a lot of them are getting killed more often, right? Because there's less hiding places. Therefore, the predators are going to eat them. So again, you don't need to study those things. But those two graphs, I love them that they put them together because one shows how population density can lower birth rates, and the other one shows how population density can increase death rates. Any questions about that slide? All right. So that was density dependent factor. Let's talk about the other one, the opposite, density independent. As you might imagine, if density dependent factors are where the intensity is related to the population density, then the opposite is true of this. It is when the intensity is unrelated to the density. And again, I'm not going to ask you, probably not going to ask you the definition. I'm going to give you an example. You need to recognize it. So some factors include changes in weather or climate. Let's say we had an ice age, right? And then the hottest it got in West Virginia after the ice age was 0 degrees Fahrenheit. The squirrels on WVCU's campus cannot survive that. So it's going to kill, if that happened, if we somehow hit an ice age, it would kill 100% of the squirrels on WVSU's campus. Whether there's a high population density or low population density, it's going to kill every single one of them. Same thing if you drop a bomb. This is more likely, unfortunately, these days. If there's a nuclear war between us and North Korea, China, Russia, whatever, and a nuclear bomb is dropped, whatever size bomb it is, it's going to kill 100% of the people within a 1 square mile, again, depending on the bomb, 1 square mile, everyone's going to die for that 1 mile radius. Doesn't matter if there's a few people or there's a lot of people, they're all going to die. That would be a density independent factor, right? Doesn't matter the population density. Anyway, your book also talks about things like fires, floods, storms, right? So if Kanawha State Forest burns to the ground next week, it's going to kill, 100% of the huckleberry bushes. Whether there's a lot of them, or a few of them, either way, they're all going to die because the whole forest is going to burn. Does that make sense? You guys see the difference between density dependent and density independent? Okay. I won't even talk about that. That could just get more confusing. In the long term, I like that your book points this out. Populations are regulated by a complex interaction of density dependent and independent factors. So again, let's take a step back and talk about why we're even talking about this, because this whole chapter is talking about studying populations and studying what controls the growth of a population, right? So if we're talking about if you're studying a population of, sharks, great white sharks, and you're looking at the things that are limiting their population, you're going to be looking at density dependent factors and density independent factors. Right? They both affect a population. So obviously this isn't a test question. This just kind of sums up the two things we've been talking about, brings them together. That brings us to population cycles. We can talk about this one really quickly. This one's very simple. So population cycles is kind of like we're talking outside of exponential growth or logistic growth. In a sense, I feel like population cycles should have come after logistic growth and exponential growth, but here we go, population cycles. The only one your book even talks about are boom and bust cycles, and you need to know what a boom and bust cycle is. And again, in my opinion, this should be taught with exponential growth, logistic growth, and then the third one, in my opinion, is boom and bust. So again, exponential, the population explodes. Logistic, it explodes and then levels off. Boom and bust, it explodes and then crashes, and then explodes and then crashes. And that's what you need to know about a boom and bust cycle. It explodes and then it crashes. Yes, it may be caused by these things, but I'm not going to ask you about them. Winter food shortages, right? So the population explodes in the spring when they're in the summer when there's a lot of food, but then the winter comes and the food goes away, so the population crashes. And then the spring comes back and the population explodes, so on and so forth. I do like that your book talks about this as a very classic example of boom and bust cycles, because in this case, we're looking at two different populations, and you can see how they're related to each other. How like when the snow shit, the hare population explodes, and so does the lynx population, the lynx, because they eat them. And eventually, that thing's running out of food, plus the lynx are eating all of them, so it crashes, and then so does the lynx population. You can see here all that's showing, though, is a boom and bust cycle. It doesn't go up and stay up like exponential. It doesn't go up and level off like logistic. It goes up and crashes. It goes up and crashes. And yes, sometimes two different populations are related to each other that way. If you download the PowerPoint, you can watch this little video that shows this in action. Perfect. The last word for attendance will be pests. And that's it. And I will be a little late for, I can't think right now, sorry. Office hours. Again, no lab in person today, or this week at all. We're not meeting for lab. I'll be on office hours probably at 9:05, 9:08, somewhere. It normally starts at 9, but I would be a little late today. I've got to get those code words for the Taylor Swift tickets for my wife. So I'll be on my office hours, but the radio is going to be playing, and if you try to talk to me, I'll be like, hold on, not yet.